Let's continue in 1.5 on elementary matrices. Initially it was defined in 1.4 in the book, but really not needed until we get to 1.5 and discuss concepts of inverse matrices. So here's the idea of an elementary matrix. We can represent elementary row operations, interchange rows, multiply a row by a constant, and add a multiple of a row to another row by matrix multiplication. And what we use is an elementary matrix to do that. So an n by n matrix is called an elementary matrix if it can be obtained, like created, from an n by n identity matrix. And this is critical too, by a single elementary row operation. So you perform it on the elementary matrix and to the identity matrix, and then that's an elementary matrix. It's a little weird how to do it. You won't have to get like crazy proficient on how to make these and multiply matrices to make things happen. It's really the understanding that they exist, and we could figure it out if we have to. And then we're going to use it for probably for more proofs and ways to define things that they exist, essentially. But we do need to have a basic understanding of them to know what's going on. So suppose you start with, so let's look at some examples. And suppose you start with the identity matrix. This is what, a 3 by 3 is 1, 0, 0, 0, 1, 0, 0, 0, 1. And let's suppose I want to multiply by a constant. So if I just did like 2/3 row 2 and put it back in row 2 to the identity matrix, then I'd end up with this. So I'd end up with 1, 0, 0, 0, 2/3 0, and 0, 0, 1. Now, that operation, if you multiplied by a matrix, would do that same operation. So now if you took that matrix and multiplied by like an A, then it would multiply that row by 2/3. So it's like an actual operation, actual matrix multiplication. So this is an elementary matrix. So I'll just say yes, an elementary matrix. And let's suppose, so we'll call that E. So what about this one? So this one are kind of going a different way. Suppose I have 1, 0, 0, 0, 5, 0, and 0, 0, 0. Is that an elementary matrix? So can I obtain that matrix by a single elementary row operation? Well, you'd have to zero out this, and well, there's really no way to do that, huh? And then you have to get 5 there. So don't think too hard here. No, you can't do it. Okay, so that's not an elementary matrix. You can't get that matrix from the identity matrix by doing a single row operation or a single elementary row operation. So let's look at these examples. We'll be multiplying matrices and things like that, just to kind of show you what's going on. So suppose you have 0. We're just going to do this product, see what happens. So 0. So you can do this by hand, but let's have your calculators out to test these as well. Speed things up a little bit. 0, 1, 0, 1, 0, 0, 0, 0, 1. All right, so is that an elementary matrix, and what did I do? Okay, and so that is interchange what? So that's interchange row 1 and row 2 is what I did in the elementary matrix. In the identity matrix. And let's see what it does to our matrix in question. So interchange row 1 and row 2. That's kind of redundant the way I wrote that, but so I'm going to interchange those and then do the product and see if it actually does that. So do this by hand or a calculator at least and see what happens. Or a computer, whatever. So if you do that product, and I'm not going to go through the whole thing, but just you go across and down, across and down, and across and down. And when you do that, you'll see you get this. Okay, so the first one will end up being the first row. So it actually does the same operation. Okay, and you need to check this. I'm not going to go through the details, but check this and see if it works. Something I'd have you do in class to verify either on a calculator or by hand. Okay, so check that out. Okay, and it works. So I interchange the rows in the identity matrix, and then that's when you do the product, that's what it does for the other matrix. Something you may try is put this over here and see what happens. See if it changes the same thing or not. Okay, 2, let's do this. Actually, let me put this consistent. Let's put this up here. And then bring this down a little bit. I'll tell you what to do ahead of time, and then we'll do it. Bear with me for a second here. Fast forward. Did I tell this class yet? It helps to fast forward my videos if you're just kind of seeing what's happening. Do like 1.5 speed. If you're copying everything down, then it works better. But okay, so 2. Let's do a constant, which I think you should copy everything down, but sometimes you're just reviewing, So constant multiple by row. So constant multiple. So yeah, that's fine. I had more stuff written down, but it doesn't matter. Okay, so let's say you had 1 0 0 0 1/3 0 and then 0 0 1, right? So that's not changed at all except for a product in row 2. And then take a matrix. And did I use the same matrix? I think I did. No, I changed the matrix. So 1 0 -4, 3 -6 9, 1 3 5, and then again use a calculator or computer or by hand. Ideally you do this by hand, and you see that it ends up being a constant multiple of row 2. So the first one doesn't change because you get 1 times this, everything else zeroes out, and then 1 times that zeroes out, and then 1 times that and zeroes out, and that's what your entries are. The second one, again, 2, 0 times that is 0, and then 1/3, 1/3, 1/3, and then everything else zeroes out. And so, not too difficult to do by hand, but sometimes I don't want you to get too caught up in some of that minutia stuff. Just need to practice it and understand what's going on. So you do get that. So you verify that it actually does multiply by that constant. So it's kind of, so picture what's happening. We can do the operation of row reduction or elementary row operations when by these elementary row operations. Now, our goal is not to like do this entire row reduction by a bunch of products, although you could do it. That's the idea, is that it can be done, which allows us to prove other stuff. But I'm not going to like ask you to do that. That's kind of wasting time. All right, so next is the tougher one, right? It's the constant multiple and then add. So let's suppose, so this is 3. We're going to make it just a 2 by 2. Let's let A equal 2, 3, 4, 7. Like that. And then we're going to perform negative, try it, sorry about that. Negative 2 row 1 plus row 2, and then put it back in row 2 by matrix multiplication. So theoretically, we do that with one operation. So let's take the identity matrix 1, 0, 0, 1, and let's do that operation to the identity matrix. Okay, so we're going to do let's see what negative 2 row 1 plus row 2, and then we're going to place it back here in row 2. Okay, so then row 1 does not change. So perform this on the identity matrix, and when you do that, you should get negative 2, and then when you add, you get a negative 2. Okay, and then you negative 2 here is 0, and then you add it to here, and you just get a 1. So this just becomes negative 2, 1. And we'll call that elementary matrix 1, E1. And so now take that matrix, E1. So now we're going to perform this operation. We're going to do E1 times A. So that's going to be 1, 0, negative 2, 1 times the matrix A, which is 2, 3, 4, 7. Now, this is what I'm going to do. Before you do that product, let's do the operation on A. So let's take A. So A is 2, 3, 2, 3, 4, 7. And let's do the operation like I just said there. Negative 2 row 1 plus row 2, and place it back in row 2, and then see what you get. So we're not touching, whoa. Sorry about that. It's my palm at the bottom of the screen messes things up. So we're not touching row 1, and so negative 2 row 1 gives us 4, and then you add it to row 2 gives us 0, and then negative 2 row 1 gives us negative 6. Sorry, I'm trying to point here. Let me back up. I can try to point. So negative 2 row 1 gives us, right there will be a negative 4, and then when you add, you get 0. Okay, let's do that again. Negative 2 row 1 here gives us negative 6, and then when you add, you get 1. Okay, so that's what we should get when we do that product. Okay, so try it. And let's just do this one together, work it all the way out. So it's first row will be 1 plus 0 is still 2. Second one is then a 3. And now it's negative 2 times that plus 4 is 0. Well, of course it worked. I'm telling you it works. Negative 2 is the 6, and then the 1 is the 7. Add, and you get 1. So the product of that is the same as this operation. This is kind of an operation we do in our minds, and we just do it. This is an actual product. So the whole point really to this is saying that those elementary row operations can be done just by matrix multiplication. Once we have that, then we have other properties to contend with. We have all this stuff back here. What about inverse matrices? What about those products of identity matrices and things like that? Okay, so that's where we're heading with this stuff. So hopefully that was a good way to show that. Let's see. So look at this definition next. So this is a definition we're using with elementary matrices. And we say, so let A and B be M by N matrices. Matrix B is what we call row equivalent, just like the elementary, it's like doing the operations of row operations, of elementary row operations. So we call that row equivalent to A if there exists elementary matrices E sub I, so I goes from 1 to N, such that B is equal to this product of elementary matrices, E, En minus 1, etc., down to E1, or I'll say that E2, and then E1 times A. And so basically, it's just, all that's really saying then is that you have A and you do row reduction and get B. Well, instead, let's just use these elementary matrices. That's the concept, and it can be done. Okay, next theorem. If E is an elementary matrix, then its inverse exists. Or I'll just say E inverse exists. So in other words, all elementary matrices are invertible. So let's just write that down, huh? This is probably a good way just to say that. So all elementary matrices are invertible. Okay. So, example. We'll get into actually finding elementary matrices a little later. I mean, finding inverse matrices a little later. Same section, but just not now. So suppose you have this matrix. This is an elementary matrix. Oops, wrong one. So 1, 0, 0, 0, 1, 0, and this is the one I changed, negative 2, 0, 1. So that would be a row operation. So to obtain that, we did negative 2 row 1 plus row 3, and we put it back in row 3. Okay, verify that. So the question is, let me, no, that's fine. The question is the inverse this? 1, 0, 0, 0, 1, 0, 2, 0, 1. All right, so is that the inverse of E? So are these inverses? Would be the question. So how would you test that? What do you do to test that? Well, you got to test, right? E times E. E inverse times E is I, and vice versa. E times E inverse, do you get I as well? So you got to test both directions. We'll just do one, but that if you can show that, then they are indeed inverses. So I really can't say it's an inverse until I know it's an inverse. But that's just the operation I want you to check out. So so do that. Do those two matrices and do the product. And so we'll take this matrix. That's okay. So take this matrix and then do the product. Let's shrink that a little bit with this matrix and see what happens. Okay, so you do those products, and what do you need to get for them to be inverse matrices? Okay, so you go through it like that. Next one. So the first two give you the same thing back. It's the last one that's really in question. So it's this times this. And so you get -2, 0, and then -2, +2. Yeah, so -2, and then so it's this one, and then you do this again, and then this again, and you'll see you'll get a -2 and 2 to give you that 0. So check it by hand and or by your computers, and indeed you will get the identity matrix. Okay, so that's equal to I. So you check E, that was E, yeah. So check E inverse E as well, and you'll get I. So therefore it's true. So therefore that is an inverse. That doesn't prove anything, right? That just is an example. Basically, it should be pretty clear. I mean, you're just doing one operation to get its inverse from I, and it's going to work. So look at, see if the book proves it, but we're not going to go through those details. We have other details to go through. Okay, next one is this theorem. So theorem, I don't think it has a number. So this one is just a property, but it's a theorem. So a square matrix A is invertible if and only if it can be written as a product of elementary matrices. So it goes both directions. So if it's square, it can be written. And if it can be written, it is, invertible. If it's invertible, it can be written. And if it's can be written as a product of elementary matrices, then it is invertible. So it's both sides. So if and only if it can, or A can be written as a product of elementary matrices. So I'm not going to go through all the little details of this, but I'm going to give you an idea. So when I give you the idea of a proof, I say just PF is like poof, and I put a parentheses. So I put quotes around it and say I'm giving you the concept. So we want to be able to say A is a product of identity matrices of elementary matrices like this. Okay, so we could show maybe one side. Let's suppose A can be written like that. Then is it equal to I and vice versa? So the idea is what we get is this product. So you get this product E1, E2 down to E sub n. And we're look at that inverse times A. But A, we're saying is invertible, or it can be written like that. So that would be E1, E2 down to En inverse, and then A would be E1, E2 to En. So when you do that product, what actually happens is, just like the transpose, these all commute, and you end up with E inverse E1 next to each other, which becomes I. But that's essentially how you start working this out to see if it's going to be the same. So you check it out. I mean, it's in the book. They do that proof, but I didn't want to go through all the details right now. But that's how you can work it out and show that it's invertible. So the whole key is that you're using elementary matrices which are themselves invertible. That's really what it boils down to. And then you got to work out the details. Okay. Last thing before we stop and move on to finishing 1.5 is this theorem. So this theorem is 110. This one we will go through in detail. Theorem 110, 1.10 says if A and B are invertible, of size n, then AB is invertible and AB inverse, that product is AB inverse, must equal B inverse A inverse. It's like you got to commute those. Okay, so because we're saying A is invertible, that gives us a lot of stuff. So that's really where it kind of boils down to. We will not have to use elementary matrices to do this proof, thankfully. Okay, but let's look at the proof. So when doing a proof like this, we need to assume that A and B are invertible, right? So it's if this is true, then this is true. So you have to assume the hypothesis and then show the rest. So if the first part's false, then you could say anything you want. So again, assume A and B are invertible. Okay, so then if it's invertible, then let's say what we got. What we got is then A inverse and B inverse exist, I mean, that's the definition of invertibility, that those exist, and then you have the product is I, right? We will show that B inverse A inverse is the inverse of AB. And therefore equal to AB inverse, because remember that whatever is here inverse by definition is the inverse of that. So the inverse of AB by definition is this. The real key here is that it's not just exist and it's this, it has to be this form. Okay, so once we show this behaves as an inverse, then it must equal that. So I'll just say, and therefore, this is a little side note, and therefore equal to AB inverse. So we basically just start off with the product, show both sides, and it works out real nice. So check this out. So you have A, B, then I'm going to multiply by B inverse A inverse. Now I'm going to associate, because you have associative property. That's B times B inverse A, which is then A I A inverse. This is the inverse here. Which, of course, then is just A times A inverse, which is equal to the identity matrix, I. Similarly, we do the same thing. I am going to show both sides this time. So if you have B inverse A inverse times AB, you perform really the same thing and associate B inverse A by association of matrices, which is B inverse I times A. Let's put those together. And that's an inverse. Wait a second. Okay. So that's I. And so you get B inverse I times B, which is just B. So that's B inverse B, which is equal to the identity matrix. So therefore, B inverse A inverse is the inverse of AB. But we just proved earlier that inverses are unique. So we're calling this inverse like whatever that product is, let's call it C. Well, the inverse of it must be just that, or AB inverse. So therefore, B inverse A inverse must be AB inverse. Okay, so since inverses are unique, B inverse A inverse must equal AB inverse. And how inverses are defined. by the definition of inverse matrices. Okay, so that gives us a way to handle a product of more than one matrix and its inverse. And what do you have to do? You have to basically commute them before you do the products. Okay, so all right, we have a number of things to do next. Cancellation of inverse matrices, the matrix equation, sorry, and the uniqueness of the solution. And then another big thing to do, which we got to practice again, kind of like elementary matrices in row reduction, we got to find the inverse matrix, how to find an inverse matrix. And that'll wrap up 1.5. So probably one more video.